Hello everyone, and in this video I'm gonna talk about breaking the symmetry, let's say spontaneous symmetry breaking. But first we start with Landau theory. And how did Lev Landau came up with the idea of spontaneous symmetry breaking? Um, First, we start by imagining a magnet whose spin can point either up or down. So imagine you have a magnet. Let's suppose this is a magnet, and you have the spin here pointing up and down in a different directions. Now, this magnet, we say that it has a symmetry. So it is well known that at high temperatures, the spin is aligned in some directions. And this tells us that the average of the magnetic moment is zero. Now, if you flip this by 180 degrees, so if you flip the spins, so those that are pointing up now point down, and so on. So you're gonna have down, you're gonna have up, down, down, up, and so on. So this configuration still has a symmetry. So the average of the magnetic moment still is zero. So the symmetry, it's not broken here at some high temperatures T. But it is found experimentally that when cooling the system at some critical temperature Tc, the system undergoes in what is called phase transition, and the magnetization and becomes non-zero and spins, and the spins can align in some direction. And we have, so it may be that they are aligned all up, and it may be that they are aligned all down. So the direction which the spin is aligned could be either up or down. What we don't know is that we don't know from the Lagrangian. So we might have a Lagrangian for this system, but we don't know. On which way they're gonna go, and this is a bit strange. Now, so this was the original symmetry. So this was the original symmetry of the system, and this is the broken symmetry. Now, so Landau theory. Now, how did Lev Landau thought about this problem? He used what is called free energy. So free energy in statistical mechanics is defined by U minus Ts. Equilibrium in thermodynamic systems relies on both minimizing the internal energy U. So this is the internal energy, and maximizing the entropy. So the equilibrium comes from minimizing internal energy and maximizing the entropy. So somehow we need to minimize the free energy. So we need to minimize free energy. Now, what Landau did, it's that he took it he took a guess of an equation and wrote it as a power series: f0 plus am squared plus bm to the fourth, where m is magnetization field. Now, A and B are free parameters, and but they might depend on the temperature. So they might, but it's not necessary, and we can leave them like that. So this free energy, it has a symmetry. So if you flip the sign, you still you get the same answer. Now, let's suppose that A is a positive. So for A positive, we have the energy shown in the picture, which might be like if you plot, for example, for A positive, you have the quadratic function, simply as that. So this is when A is positive, for A bigger than 0. And which is for high temperature regime. So this is the high temperature regime. Now, what happens if A is smaller than 0? Then we have the function is plotted like, so maybe I cannot draw it properly, but it should be like something like this. So now we have two minima at non-zero values. So these are two minima we have, and these are non-zero values, and these are gonna be m equals plus or minus m0. So let me take this plot and put it here. So we have two minima at non-zero values. Now, the m equals to plus m0, which is this one, and this is minus this one. So m equals to m0 corresponds to spin aligning in the up direction. And m equals to m minus 0 in down direction. Now we had the previous minimum that was the minimum was at m equals to 0, which it is called now. It means it is here, which is called metastable equilibrium. Now suppose you have A equals to A0 T minus Tc. So we said that the parameters A and B may depend on the temperature, where A0 now is a constant. So and yeah, we take B, which is independent of tau. Then if A is bigger than 0, so if A is positive, we have T smaller than Tc, and if A is negative, we have Tc smaller than we have T smaller than Tc. So this here predicts the phase transition at temperature. So this here predicts the phase transition